So I've done failure analysis for around 20 years plus. This presentation is about battery management systems, how management systems keep cells living in the world they want to live in. So battery cells have specific parameters in terms of, and I'm talking lithium ion here, the maximum voltage, the minimum voltage, the maximum current, both in and out, and maximum and minimum temperatures. So one thing I want to state here is that this is not fire investigation information. There's many fires nowadays that are blamed on lithium ion cells in larger fires where there are many different products. This presentation is based on work that I've done over the years where a client has asked my company to help them understand what went wrong. That's why I was involved in the Sony recall. So when we are doing the work specifically, which is not what this presentation is meant to be about, these are some of the things we do to document what we're seeing, to try to generate hypotheses for why a lithium-ion battery has failed. Most of this is outside the cell because I'm an electrical engineer, and a lot of my work has been on testing battery management systems and what they do to protect the cell, to keep the cell living in the world it wants to live in. So a lot of this has to do with looking at the cells. Cell mass is important because often the first cell that fails reaches a lower maximum temperature and pressure because it's at room temperature when it fails. If it does collateral damage to other cells, then those cells fail at higher temperatures and pressures and lose more mass. So most of you probably understand this information, but when we're charging, lithium ions move from the cathode to the anode, and electrons leave the cathode through the charging loop, which means current is traveling into the positive terminal of the cell, and the anode acts like a sponge, and the lithium needs to diffuse into that sponge as the battery is charging. So because of that, if you charge it at an excessive current, the lithium piles up kind of like water being poured onto a sponge in your kitchen, and it can't absorb into the sponge. So the trickle of lithium needs to be slow enough so that the anode can absorb the lithium ions into the carbon. When we're discharging, the lithium ions travel back and basically oxidize the cathode, giving up an electron to rejoin with the crystalline structure of the cathode to release the energy they've stored by becoming lithium metal in the negative electrode, the anode. So that's how the energy is stored and then released in lithium ion cells. Overvoltage protection is very important in cobalt-based cathodes, and I'm contrasting cobalt-based cathodes, which could be NMC or other cobalt materials. Lithium cobalt oxide is the traditional cathode material. It's called a half lithium system. So if more than half of the lithium is removed and the anode is made to be just big enough to absorb half the lithium in the cathode, then the cathode begins to degrade and generate gases, and eventually you get overcharge, and eventually possibly a severe reaction where the cell goes off. So a traditional laptop technology, which is pretty much the most advanced battery management systems that you have multiple redundant protection against overcharge. You have the charger, which is not listed here as something that, when working with the number of cells in series, cannot get the cells, if balanced, over a certain voltage, and therefore, if balanced, the cells cannot get to a high enough voltage. If the charger were to provide excess voltage, or if you had a severe imbalance in the voltage in the cells, such that the charger cannot tell that, well, say 12.6 volts in a 3 series battery, well, we've got one cell at 3 volts and one cell at 4.5 volts in that 3 series battery, and now we're going to just keep charging. So what they have is an analog front end that's fast acting, that opens a switch, and that switch is called a CFET, a charge field effect transistor. If that doesn't work, then you've got a microprocessor backup that could open that same switch. If that doesn't work, there's typically a completely independent circuit that is watchdogging the cells that can open a 3-terminal fuse and permanently disable the battery. That 3-terminal fuse is electronically controlled from that watchdog, and it operates by generating heat and internal resistors. And one technology will put that 3-terminal fuse on right on the FET switches in case they fail and generate heat, and then it will open the circuit if your FETs are now failing and generating heat. So lithium iron phosphate batteries are advertised as safer. They're a 1 lithium system, so when you overcharge, so to speak, a lithium iron phosphate battery, they run out of lithium and stop conducting electrical current. However, because the open circuit voltage of your charger needs to be higher than your end voltage of your cells that you've designed the cells to reach, in some cases that's 4.1 volts, because you can afford to lose some of the capacity in your cell phone or your laptop, for example. You want all that capacity. So a typical output voltage without a load, an electrical load where you're conducting current, may be 0.1, 0.2, 0.3 volts higher than your end state of charge. So for a 12.6 volt battery, which is 3 series, 4.2 volts each, you may want about 13 volts to lift that battery up to that voltage, so it can actually continue to push current, and then you do your CV charge profile and cut off from your charger. When you stack up a lot of lithium iron phosphate batteries into, say, a 100 series battery, well, that's about 30 times a 3 series battery. So you're going to need 30 times that 0.4 volts that I just mentioned. And I'm doing math now, but basically you end up with a much larger headspace on your open circuit voltage. And then when a lithium iron phosphate battery runs out of ions in one of the cells, because it's a race condition, then you get the open circuit voltage of the power supply right across the separator within the cell. And that can cause dielectric breakdown. And then lithium iron phosphate batteries are just as volatile as any other type of lithium ion battery. I'm sorry that I can't take questions. I'm going to have to answer in chat, I think, because no matter which device I get on, I can't hear you or you hear me at the same time, which is difficult. I tested it on the platform and it didn't work. It worked when I tested it, but it's not working while I'm live here. Balancing circuits, if you've got a high energy battery where you're trying to make your device last a very long time, 10 hours for your cell phone of continuous use, for example, then you may not need to balance very quickly because your current, both in charging and discharging, is relatively low into that electronic consumer product. A drill battery is completely different because you need a lot of power. That's called a power cell. So the way the circuits work is that the chips, generally the ICs, the integrated circuits, have a balancing circuit built into their actual structure, but they balance very slowly. If you need to balance cells much more quickly because the current rate is much higher, then they also act as a sense, but an output to turn on external switches that then detour current around the side of the cells that are near maximum voltage so that the cells at lower voltage can catch up in voltage and end up at the same end voltage. The amount of current is controlled by the resistors that are in series with the external switches. So as your battery pack with multiple cells age, they change in capacity from you could say perfectly balanced capacity, say 2 amp hours per cell, and they've all been matched when the pack is manufactured to a variety of different capacities. So maybe the worst cell drops to 1.8 amp hours, other cells stay close to 2 amp hours. That lower capacity cell swings in voltage faster because it's a smaller bucket to collect energy and to release energy. So the voltage, it will start to potentially trigger protection circuits instead of charging ending naturally or discharging ending naturally by design, by the charger controlling that, or the capacity measurement of the amount of current that's leaving the pack that's related to capacity, where the pack says I'm fully discharged, like your phone says 0%. And when it does that, it turns off on you because the phone says my battery is fully discharged. This is a communication issue. I'm turning off. It's not because the battery's gone below, say, 3 volts per cell, or in a cell phone, the 1 cell. So under voltage protection, have a particular issue. When the anode runs out of lithium to provide to the cathode to give you the electrons that are the current that run your electrical device, the next contributor in line is copper. So copper will then start to participate as an ion to oxidize your cathode. When that happens, the copper, which is what the carbon is layered onto to make the anode, the copper is what collects the electrons. It's called a current collector. It will start to degrade and fall apart, and then your cell degrades, and now you have a potential severe failure, or you have a potential cell that's not working anymore. I have typical settings for what the electronics in the BMS will cut off discharge current at if the other systems for discharge in, say, your cell phone stop allowing discharge current because it decides your battery's at 0%. One thing that I'll say is that I many times come across folks that think a 0% state of charge is a battery that's at 0 volts. It actually is pretty much out of lithium ions in the around 3 volt range. If you keep drawing the same amount of current out of the battery at 3 volts, the voltage will drop very quickly. So you will cross this 2.5 volt threshold in a matter of minutes. So that's another thing I wanted to point out. Overcurrent is generally not a concern during charging. Overcurrent is during charging. Current is driven by the difference between the output voltage of the charger. I mentioned, say, 13 volts minus the voltage of the battery. I mentioned, or say it's 12 volts. 13 volts minus 12 volts over the loop resistance is the amount of charge current you're going to get, except for that the rail of the charger will limit that current during your constant current phase of charging. Now, on discharge, we've all heard about the monkey wrench on your battery terminals in your old car battery. Yeah, they will give you what you want. So, if they see, if the protection electronics see an overcurrent, similar things happen. It's called the discharge FET that turns off. The certain designs now have a communication circuit that communicate to a master controller that will then bring, say, a rack offline because we've got a problem in one of our modules, for example. And those are protected with only fuses. There are designs now where there are no CFETs and DFETs, the switches that stop discharge and charge current. These circuits will balance cells, but they are simply crying for help to the master controller to take them offline. So, temperature protection. These are typical values from cell data sheets. It is surprising to some folks that you can withstand discharge at 70 degrees C before protection electronics will kick in and stop discharge. On charging, they are spec'd for lower temperature levels to interrupt discharge, to interrupt charging. And I think I already covered the bottom bullet points here in terms of integrated BMS like you might find in a laptop or a cell phone stopping discharge at these temperatures. And maybe some of you have experienced leaving your phone in the sun and it not working. That's because it's detecting an excess temperature and has disconnected its battery from the phone. So the diffusion concept, where the lithium has to roll into the carbon sponge, so to speak, the diffusion slows down at low temperatures. So these are typical traditional values for discharge and charging. But if you're below 0 degrees C or 32 degrees Fahrenheit, the lithium diffusion becomes a concern. Of course, there's margin here, but at your normal charging rate, the lithium ions cannot get into the anode fast enough. In other words, the sponge gets a little too cold and the water starts rolling off the edges. When that happens, you can have lithium plating. I think there was a public presentation given about the Samsung phone issue with the signs in the airport where the edges of the anode got bent by the size of the cell pouch, and lithium plating in that area led to an unacceptable rate of severe failures of those phones. So lithium plating is one of the main causes of severe failures in lithium ion batteries, and charging at low temperature can cause that across the entire surface of the anode in the jelly roll, or these days stack cells. So I'm almost done. I was in a bit of a hurry. There's a few other things that aren't in my presentation that I wanted to point out that are failure modes that we've seen in the failure analysis we've done over the years, or root causes of failure, I should say. The protection electronics generally work right. They do their job to keep the cells in the world they live in or want to live in. Therefore, most often, and I mean the vast majority of lithium ion battery failures have to do with the cells themselves having an internal fault that the protection electronics cannot control. And there is a non-zero failure rate for lithium ion cells that cannot be eliminated. The problem is on the next slide, is that we accept the risk. This is my putting on my reliability hat. The toughest engineering risk assessment reliability decisions come down to likelihood and severity. We all know that the severity of a lithium-ion battery is not good. There are stories in the news generally that you can look up, and they happen all the time. E-cigarettes, hoverboards, the Sony recall, etc. So the question becomes, how do you reduce the likelihood to reduce the risk? You can't reduce the severity of a lithium-ion battery failure. You have to do everything you can to reduce the likelihood. When the likelihood of failure rises to an unacceptable level, then you hear about the recalls. But we all take the risk of having these cells around us, these batteries around us. I carry my cell phone in my pocket and accept the risk that it could catch on fire. So, you know, as a society, we are accepting the risk of what we're doing in the Volta Foundation, that if you're into lithium ion batteries, traditional types, you're not going to have zero failures in the field. There are going to be some severe failures. Like I said, this presentation is based on failures that have not started fires, but that were gotten back for failure analysis. So one other, I think, esoteric root cause of failure for lithium ions that I want to bring up is specifically for pouch cells. Pouch cells swell. They're traditionally known as lithium polymer, but they swell over naturally over the cycling life of their time in the field. When a pouch cell is made, it's an aluminum foil wrapped around the jelly roll or the stack with a polymer layer on either side as insulation. When they cut that, there's an aluminum edge that is between the polymer. If that aluminum edge gets referenced in the outside electrical circuit to the negative tab, in other words, the ground of the system, the phone, the laptop, larger batteries, if it gets referenced to, say, earth ground chassis, which B negative is generally connected to, then the aluminum the reason they can't use copper or aluminum as the negative electrode and have to use more expensive copper is because aluminum is a less noble metal, and it will start to participate, like the lithium ions, in the discharging reaction, and then you'll have corrosion of the pouch and eventually holes in the pouch, and then electrolyte leakage. And this is something that we've analyzed and found in the field in the past. So that's something that's not commonly considered when it comes to battery pack designs, in terms of making sure your pouch edges are nowhere near any kind of conductive metal in a product, because that conductive metal is always at battery negative, and that will make the aluminum pouch at battery negative, which will destroy the cell. So it may not be a severe failure mode, but it can be. So sorry about the audio difficulties here. Let's see.